This is problem 3-148M on page 175. The lower control arm on an automotive suspension system is connected to the frame by a round steel pin 16 millimeters in diameter. Two sides of the arm transfer load from the frame to the arm as sketched in figure P3-148, which is just below, by the way. How much shear force could the pin withstand if it is made of AISI 1040 cold-drawn steel with a design factor of 6 based on the yield strength in shear? I guess if that's what's desired, how much shear force could it withstand if that yield and safety factor is desired? Okay, so reference the figure, please, especially if you're watching the video. And hopefully you understand what it's showing you. That top view, you'd be looking at the pin from the top. Let me sketch it because I think this will be helpful. So there's basically the frame, part of the frame of the car. The A-arm's coming off like this with a bolt through it. And what's going to happen is it's going to tend to shear here and here. So this is a double shear type problem. Then they also sketched it looking at it from this direction. So you see the tube here, and you see the bolt coming through, and then they've got the A-arm on either side. Now really, the way they've drawn the other figure, you'd expect these to come out and flail like this. So it takes a second to understand what they're talking about. But we're just talking about shear along those two planes for this pin. So it's not a terribly difficult problem. In fact, I'll just leave one of these up, we don't need both. In fact, what we'll have to do is talk about the design shear stress, which is the yield strength over, normally it's over the factor of safety, but in our particular case, we've got shear in two sections, so it's a double shear type problem. So there's more area basically that, make sure I'm talking about the right part. No, I'm getting ahead of myself. Go back in the book if you would. Here it is, page 158. Table 3-8. There's two factors of 2, and I don't want you to confuse them. That's why I stopped saying what I was saying a minute ago. Okay, table 3-8. They have asked for a factor of safety of 6. What does that correspond to? Impact. Would you expect impact loading on this pin? Oh yeah, every time you hit a pothole, right? Or go over a speed bump too fast, there will be impact. What is an impact? Well, it's just basically a high force over a short period of time. That's all it really is. And so this is basically the worst case scenario. And notice the design factor of 6 corresponds to dividing the yield strength by 12. Why is that the case? Well, I'll explain it. The yield strength is measured with a sample where you're pulling it apart axially. Does that make sense? Well, that's a different type of stress. That's actually not a shear stress. That is a normal stress. And so to convert the shear stress, or the normal stress here essentially, or the normal strength, to a yield, a stress, you have to divide by 2. And then the factor of safety of 6, 2 times 6 is 12, and that's where the 12 comes from. Okay, again, we'll talk about this more later when we talk about Mohr's circle and the relationship between normal stress and shear stress. They are related, but we can't give you all of that information at one time, so you just have to trust that we need this factor of 2 because this is a normal stress and we need a shear stress. Okay, so that's where that 2 comes from. The double shear 2 is going to come in later where we talk about how much area is available for shearing. Okay? So anyway, if you go and you look up the, one more thing about that table. Notice at the top that table says it's for ductile materials. So we better make sure that 1040 is a ductile material. So let's go to the back of the book on the material properties. We're interested in 1040, so page 714. 1040 cold drawn has a yield strength of 82 KSI. Notice its percent elongation is 16%. Is that a ductile or brittle material? It's definitely ductile because it's greater than 5%, right? Okay, so we're justified in using this equation in the first place because it is ductile. Now, of course, I need to look at my units. We've got millimeters, so we better read off the megapascal version rather than the KSI version. So 1040 cold drawn, 565 megapascals. Everybody see that? So 565 megapascals divided by 12. Plug that in your calculator, you find it's about 47.08 megapascal. So that's the maximum shear that we would allow to be applied to these bolts, whenever they're loaded in shear. Okay, now the area, the shear area that's available, well, there's a section of the bolt over here, which is just a round section, and another section over here, right? Notice how the area normal points this way, and the force points this way, so it's a shear type of loading, okay? So the area of shear, there's two of them, and each is pi d squared over 4, okay? So the diameter of the bolt was 16 millimeters, so 2 times pi over 4 times 16 millimeters squared. Plug all that in your calculator. If I did this right, I got about 402.12 total millimeters squared of area. So there's about 200 square millimeters on this side, about 200 square millimeters on this side that's being sheared. Bless you. I see frowns. Any questions? All right. So that's the area available. So the shear, basically what we're going to do is we're going to say, well, the design shear should just be the force over the sheared area. So we can solve for the amount of force that can be applied. So we're not going to apply all 565 divided by 2 megapascals. We're going to apply 47 megapascals instead. That way we have our factor of safety of 6. So that's what goes in here. And to calculate the force, all we have to do is multiply that design stress by the area that's available to take the stress. So there it is. So plugging in all the numbers, I'm going to plug in gigapascals, so 0.04708 gigapascals, if you want that many decimal places. And then 402.12 millimeters squared is the total shear area. Perform the multiplication, you find this is about 18.93 kilonewtons. And so the maximum impact loading would be about 19 kilonewtons that we could apply. Okay. Anyone have a feel for kilonewtons? Me either. Could you convert it to pounds? Could you convert it? You could definitely convert to pounds force. And I'm determined to find the conversion factors in this book. I know he must have them. Anyone know a page number right off? Conversion factors, page 743. Found it in the index, or the appendix. 743. This is a page that you should probably mark, because you will most likely reference it frequently, but just for the sake of getting an intuitive feel for how much force this is, let's convert it to pounds force. So let's see, force, here's newtons and pounds force. It looks like there's 1 pound force for every 4.448 newtons, and of course kilonewtons to newtons is pretty easy. There's 1,000 newtons per 1 kilonewton. So the kilonewtons go away, the newtons go away. Plug that into your calculator, please. And don't forget, we still have a kilo here. So this is going to be kilopounds, not just pounds. Okay? Or no, wait a second. I take that back. Take that back. We crossed off the kilonewton, so it won't be. I was wrong. It'll just be pounds force. About is that about 5,000 pounds? Did I do that right? $42.55. Okay. Is that a whole lot of impact loading? I don't think it is. I mean, the weight of the car is on that same order of magnitude. So that doesn't look like a very strong, yeah.
What's the units behind the 4.448 underneath the?
This is newtons. It's an N for newtons. I got it from the conversion factors on page 743. Good question. Anything else? It looks to me like this is undersized, but that's my opinion. Questions, comments?